All right, welcome everyone to the next seminar. I'm very excited today that we have Cliff Burgess, who's joining us from Canada, to tell us about the gravity of particle physics. So I think many people in the audience, I see some familiar faces, will probably know Cliff. Cliff is a fairly renowned theoretical physicist who's done a lot of very interesting, important work. One of the reasons he may be familiar to the PhD students here is he wrote a very nice textbook on effective field theory, which is part of their reading course a few years ago. So some of the PhD students remember that fondly. Yeah, so Cliff is here to tell us about, I guess, some recent work on gravity and particle physics. So I will leave it now in Cliff's hands. So thanks very much, Cliff, and take it away.
Thank you. Thank you very much for the invitation. My only regret is not being there. It's one of the miracles of Zoom that we can do this at all, but it's also one of the sad things of not having the face-to-face conversations. I'm going to pause and just put a timer on here. So I'm aiming for 50 minutes. Is that right? Or okay, good. So timer's on. So again, yeah, thank you very much for the invitation. I'm going to tell you, it's actually partly recent work, but it's really a journey of more like 20 years that this is a part of. And it's the story, the gravity particle physics, what that's supposed to convey is particle physics there is a proxy for physics at high energy. And gravity, I'm thinking of tests of gravity or cosmology, which is at the lowest energies that we really have access to. And particularly if you've been working through the book, the effective field theory book, you know that it's kind of a surprise that they have anything to say about each other at all. Normally condensed matter physicists don't spend a lot of time worrying what the string theorists are doing, and that's because decoupling ensures that if the string theorists get QED right, they're going to get it all right, and all of condensed matter physics right, pretty much. So there's kind of an opportunity in cosmology in that that's not true. That there's information in high energy physics that seems like it's relevant at low energies, and that's kind of what the story is. And the picture is Scotland, and it's supposed to convey. Let me make sure I can change the slides here. It's supposed to convey that I want to make a distinction between what I'm doing and the swampland program. So I want to argue that I'm taking the high ground. Everything I will be doing will be just the effective field theories as you would have applied them anywhere. And so that means that there are some predictions that you can make from high energies that are robust. For example, the symmetries, the chiral symmetries in QCD, and there's some predictions from high energies that are very specific and UV specific, like for example, the mass of the proton would be a very specific UV sensitive prediction for QCD. And the distinction I'm making here between the Highland program and the swampland program is the basic assertion of the swampland program is that there are some features like the existence of de Sitter space, for example, that are being asserted to be UV sensitive, and that understanding them is telling us something deep about things at high energies, and that's what makes them informative. And if you accept that, then that leads you down a direction of trying to identify what kinds of UV sensitive observables there are. I'm going to instead focus on things that are robust consequences like symmetries, but there's, I think, much to be learned that way, and it's much less speculative and I think controversial probably than the swampland program as a result. I'm glad people are thinking about the swampland program, but I just want to make, since I'm talking about UV physics and cosmology, I want to make sure that it's clear that the techniques are different. So what I will tell you that's involved with stuff that I've been doing recently has been done with, particularly the yoga model stuff has been done with Fernando Quevedo and Danielle Deneen, who at the time was an undergraduate, but who's now a graduate student in cosmology. And then the later stuff on screening with Philippe Brax. And it's based on the symmetries that we're using are based on earlier papers with Michele Ciccoli and Sven Krippendorf and Michael Kubke and Fernando as well. So here's the way I'd like to phrase. I'm going to tell you the story backwards, actually. The motivation is really coming from cosmology and what UV physics can say about cosmology, but I'm going to start actually from the cosmology side rather than the UV side to ask what kinds of, you'll see that the models I'm going to talk about are going to lead to things like scalars that are very light. And I'd like to ask, what should we expect? What kinds of interactions of light scalars should we expect to be the ones that should be competing with gravity at low energies, given what we know about the low energy limit of things? And this will culminate in the more is different. I'm stealing Philip Anderson's lovely title of his essay, but I'm going to argue here that there's been the case I'm going to make is that that multiple scalars is actually probably the more likely thing that we're going to find at low energies rather than just one. And that's not a surprise, I think, to people who come from high energies like the string theorists. But a lot of the community testing gravity and cosmology, for example, for Euclid, they have organized the way they search for tests of gravity in a different way, and for simplicity, and and very understandably, you can't test everything. So a lot of effort has been put into single scalar field models as being kind of the minimal change to general relativity. And one of my conclusions will be that that choice of a single field removes by accident the one class of interactions that are probably the most likely to be competing at low energies with gravity, the two derivative interactions. And so that'll be the first message, because I think that's actually probably the most important message that I'm going to bring. And then I'll switch to how I got into this, and that is arguments that are aimed at the cosmological constant problem, but they're really exploiting symmetries that are present in every single string compactification that's ever been done. I'm not going to do any string theory here, but I'm going to argue that there are some very generic symmetries, some of which people know about and explore in detail, in particular axions. But I'm going to argue that there's actually another class of symmetries that's almost not explored at all, accidental scaling symmetries. And there's a sense in which scaling symmetries, together with other features at low energies in string theory, I will argue, are more than the sum of their parts. So they are there's an effective mechanism for suppressing the scalar potential, contributions to the scalar potential, that the string theorists have known about since 2005, but then they buried in their literature, and none of the rest of us knew about it. So I want to tell you that mechanism. That'll be the main part of the message in the second half of the talk. And then I want to describe a model which just tries to use this mechanism, apply it to the dark energy, because that's an obvious case where we'd like to suppress contributions to the vacuum energy. And I want to argue for you that although I don't think we've solved the problem, we go way farther than anybody else does. But along the way, it implies those models, the symmetries themselves don't do everything you need, but they set up a relaxation mechanism. And so we call those yoga models because they involve natural relaxation. And you'll see that the kind of things you're led to at low energies will involve light scalars. And those light scalars, what's surprising about them to me is that they, for free, bring along features which could be relevant for the Hubble tension. They could be relevant for the hints for birefringence in a way which they were not designed to do. That's just kind of a freebie that comes off this picture of these models that were really aimed at the dark energy problem. And so it's kind of suggestive that there's many things that seem to be there for free, but you'll see that when I get there, that that's really not a final conclusion, but there's hints and prospects of interesting physics there. And part of what's slowing down the development of these models is the absence of tools. The effort that has been made to develop tools for exploring and testing gravity for light scalars, they've largely been tuned towards single field models. And so part of the problem is developing these tools. And so I'm hoping to encourage people who are involved in the tool building to put some effort into these class of models, which are very largely unexplored, which is very unusual in mature fields like particle physics and cosmology. And then the final thing I'll show you is that I think in my mind, the biggest challenge these models face is that these scalars that they predict, they want to be Brans-Dicke scalars, and they want to have couplings that are gravitational strength. And so they want to be ruled out by tests of gravity in the solar system. But so the question there becomes, the prediction is really for microscopic couplings of various particles to these scalars. And the question is, do macroscopic particles couple, like the sun or the earth, couple to the fields in a way which is just a simple addition of the individual particles? And that's the kind of physics that falls under the name of screening. There's an existence proof that screening happens in these series because black holes have no couplings at all. They perfectly screen, and that's a consequence of the no-hair theorem. But the model building that's going on now is really to understand whether or not you can evade these tests in the solar system. And my hope is to convince you that this model building exercise for scalar fields and testing of gravity is an easier problem to solve than the cosmological constant problem, and that this moves the problem into an area which hopefully it'll be possible to make progress on. Please also interrupt me at any time. I can't see the chat thing, and so if somebody has put a message in the chat, please interrupt me if you see it, because I'm certainly happy to stop along the way. Okay, so now the first part. So that I want to ask what would you expect scalar fields to look like at low energies if you're looking for tests of gravity, or I mean energy is low enough that you're seeing them, say, in gravitational waves or in cosmology, or there's some observational consequence that would be competing with the things that we do measure. And then and here is where I'll criticize the single field approaches to that have dominated the way people think about phenomenology of light scalars. So the surprise is going to be that, as a particle physicist in this business, I'm supposed to be sneering at models with light scalars because you have to understand why they're light. They're not generic at low energies. And of course, I'm not going to sneer against that. It is true that light scalars are not generic at low energies, but they can be, they can appear in certain circumstances, and usually when that's associated with accidental symmetry. So I'll be working very much along that line, although the symmetries I'll use might not be the axionic ones that people often use. And I want to go farther than that. I want to argue that people's mindset, that people assume that there will never be a solution to the cosmological constant problem, but I'm not that pessimistic about it because I think that it's hard, but I don't think it's insurmountable, and I think people have not yet explored all the corners that need to be explored. But in particular, if you do have a picture that explains to you why the vacuum energy or the dark energy that we see is as small as what we see, I want to argue that actually makes the likelihood of light scalars more, that makes them more likely than less likely. That having a light scalar and having a small vacuum energy, people think of that as being two problems. You have to understand why the vacuum energy is small and then why the scalar is light. I'm going to argue that they're the same problem, and the vacuum energy being small, actually, anything that's gravitationally coupled to a vacuum energy that's small will want to be light, and so they will be light for free. And so we should probably expect, it's not a stretch to expect if you get any, you're going to get more than one. And then I will make the case about why we should be looking for more than one, and why the program that's led to Horn-Dicke models is, I think, misguided. So what would you expect at low energies if you had a scalar field interacting gravitationally, competing with gravity? It'll come to you as some derivative expansion, and we're exploiting here the fact that we're interested in energies which are much, much lighter than the fundamental scales of the problem, the Planck scale or the string scale or whatever you think the microscopic scales. The weak scale could be anything we know about in particle physics is going to be a high energy compared to the scales relevant at low energies. So here we have a generic action, and I've deliberately taken the fields here and left them dimensionless and all these functions like the scalar potential that's here. Is there a question there? So the zero derivative terms, it's an arbitrary function. I'm thinking of it being an order one function, and I'm not assuming it's powers of field, because I want to emphasize, sometimes people say that trans-Planckian physics or large field values for scalars is somehow beyond the reach of effective field theories. And I want to argue that that's not true. That's just a popular misconception. So I'm kind of deliberately phrasing this where the size of the field, it can be order 1, it can be order 10 in Planck units, and it's not a big deal. So the fields are dimensionless. The two derivative terms are the Einstein term, and then possibly if you have a variety of fields, a sigma model term where I've got a scale f there, which is setting the scale. That would be the decay constant for an axion. And then there's some functions, the target space metric curly GAB, which controls the interactions. And then there's 4 derivative terms, and I will later on write 6 derivative terms to make a point, and so on. Now, the usual rule for low energies is pretty simple to state. It normally says that if you integrate out particles of mass m, they appear in all these, they contribute to all these effective interactions where m is appearing in the way that dimensional analysis requires. And so all of these coefficients are going to come to you as sums over particles you've integrated out. And the ones where the masses are in the numerator, it's the sum of the positive powers of the masses involved. So the biggest mass wins in that kind of a sum. Whereas if I'd written down a curvature cube term, which has a coefficient which is 1 over mass squared, we'd have a sum over 1 over mass squareds, and then the smallest mass will win. And so when I make the point later on of looking at curvature cube terms, the electron mass might be the one that's important there. It's the lightest thing you've integrated out. It's not the Planck mass if it's in a denominator. But in the numerators, it's completely natural to have large scales. The and having this decay constant for a scalar be the Planck mass is not a stretch at all. So I'm going to assume that for simplicity, because that's often what you get in actual UV completions. Now the problem is generically that the no derivative term is also, you'd expect this V scale, which is controlling the size of the potential, to be large. But if it's large, then the problem is, if you look at the field equations, which are written at the bottom there, then large values for V, if V was the Planck scale, then that would mean the curvatures in Einstein's equations would also be the Planck scale. And then the whole derivative expansion I'm talking about would not work. And so the way I'm organizing things wouldn't work. So this derivative expansion really presupposes that the no derivative term has to be small. And part of my message is that if it's small in the Einstein term, as it, in particular, a special case of that is the cosmological constant problem, but it's not just that. That also means it's small in the scalar field equation. And so it likes to come in as a smaller mass than you normally would expect. And you could ask how small. And this is how small you're generically getting. If U is an arbitrary function with kind of order 1 coefficients in it, then the typical mass you'd expect to find is V squared over F, where F was the thing in the scale in the kinetic terms. That's what you would have expected for an axion, for example. But I'm taking F be M Planck. So you're expecting something to be of the order of V squared over M Planck. And if that potential was the one driving the expansion of the universe, that's the Hubble scale. So this is kind of showing that if you've arranged for V to be small, and if the potential we're talking about is driving the gravitational physics you're looking at, then generic scalars that are coupled to it with gravitational strength, which is being set by their kinetic terms being set by the Planck scale, they're going to want to couple with have very, very small masses that are of the order of the Hubble scale or the curvature scales in your problem when you're looking at them. And that'll be dynamical if the potential shrinks as the fields evolve, then the masses will also shrink. And so having particles with masses in the ballpark of the Hubble scale is not a stretch at all if you've understood once why the potential is small.
Sorry, I have a very naive question. Are there restrictions on what the potential U of phi might look like? I mean, it looks like, at least from this analysis, that, it really doesn't matter as long as it's probably, analytic and, like well-behaved with a, proper, let's say proper minima or something like that, et cetera, et cetera.
Right.
The other question is, can U phi be weird enough that, might go through multiple minimas or something?
Absolutely, yeah. So I'm gonna make a power counting argument in the next slide, which is assuming that there's no large numbers essentially in U. So I'm thinking that U is just some function of, maybe it's sine phi, or it's just some function of phi, and it could have multiple minima. I'm not going to make many assumptions about that. But if you think about actual potentials we talk about, like the Higgs potential, there's a variety of scales there. There's the scale in cosmology. There's the Higgs mass, and so that in this language would correspond to being very large dimensionless numbers hidden inside U of phi, which are tracking the ratio of those scales. And if you have those big ratios, that complicates the argument I'm making. But I'm, for simplicity, assuming that's not present right now.
Right. Okay. All right. Thanks. Yep.
But in principle, those are definitely there. And nothing I'm going to say is going to be contradicting what you know about specific potentials that you've thought about. I'm partly trying to emphasize that, supposing U of phi, you understand it very well in the large field limit, which is sometimes what happens in string theory, then that's the asymptotic form you'd use for U. There's nothing that forces you to write U as a polynomials in phi, except if you understand the U in the small phi limit, you'd be tempted to do that. But the expansion in powers of phi has got nothing to do with the low energy limit. It's really, the issue there is as long as the potential stays at low energies for large values of the fields, then large values of the fields are completely describable in effective field theory.
Yeah, the reason why I asked is because, I mean, I can massage you to make it probably look like a pure Brans-Dicke theory or something like that, right? In principle.
You're going to see that I'm going to arrive at exactly Brans-Dicke theory.
Okay.
So when I get there, you'll see that it's Brans-Dicke theories are going to be looming large in the tail end of the talk. Okay. So now I want to argue. So that was all the derivative expansion. But you might say, well, I'm not going to do a derivative expansion. But now I want to argue that you have no options on that. Everybody's doing the derivative expansion, even if they don't believe they are. And that's because it's the derivative expansion that's justifying the classical approximation.
May I ask one?
Sorry?
So may I interrupt?
Yes, please do.
Yeah, so whenever you set decay constant scale at M Planck, it means like the cutoff in principle for this effective theory is very large. So then how you can keep, let's say, the scale of potential very low, because in principle that by radiative correction should be corrected. Like Higgs mass gets corrected up to the cutoff of the effective field theory.
Right.
Because
So
you
I have
set
this.
decay coupling very high, let's say.
So those are logically independent things. I can have a large decay constant, like the Planck scale in the Einstein term, and still have my cutoff could be below the electron mass, for example. And those are not related to one another because that's more of an issue for the terms like the one I've written here, which involves r cubed. The masses that are in the denominator, it's the smallest mass you integrated out is the one that dominates because you're adding inverses of things. But in the numerators,
right, I would agree. They can be different. For instance, in large n, then you need like large amount of species of such scalars and so on. But if you have
you don't
one,
even have to have, I can have one species, and what I'm saying is still true. So
but
supposing we're below the electron scale, then I would argue that in that r cubed term, it's the electron mass that should be there because it was really a sum over everything I integrated out, and the lightest one wins. But in the numerator, it's always the big one that wins. So having it at the Planck scale is a very conservative thing because it's saying that all the light ones are contributing to it by amounts which are much smaller than what we already have. The scalar potential is the dangerous one, and that's the one where I'm going to be heading towards for naturalness arguments. But it's true that the scalar potential, why that potential is small is the basic problem in cosmology. And that's a lot of what my talk is going to be on, is how to address that in a natural way.
sure, but then you cannot have cutoff up to M Planck, right?
I can, I claim I can. I can have my cutoff be anywhere. It could be the string scale, it could be the weak scale. Everything I'm telling you would work no matter where if I was writing this down at the weak scale, what I'm saying is true. I write it down below the electron mass, it's still true. So that part where the last guy integrating out was relevant to the small mass in front of the r cubed term. It doesn't really affect the guy in front of the Einstein term or in the kinetic term.
You mean the okay.
So I'm going to give you actual string compactifications where we'll be at low energies, and you'll see that this M Planck is actually a very generic thing to get for scalar kinetic terms. It's not that difficult to get. It's actually hard. It's harder to get axions with small decay constants. It's actually really easy to get Planck scale kinetic terms for scalars in honest to God string vacua. And in that case, your cutoff would be the scale that you last integrated out. It might be the Klutz-Klein scale. It might be the string scale, depending on the question you ask. But everything I'm saying is going to go through in that case. Later on, when I get to the point of writing things down, if you still have the question, you should ask it again because I'm claiming that it's going to work, but it's probably hard for you to see what I mean until I actually write it down. But then please do re-ask that if you find that later on it's bothering you.
Sure, thanks.
Okay. All right. So this is I'm now making the case that the derivative expansion is compulsory if you're using semi-classical methods, which everybody is in gravity. And so the way I'll show that is that we'll just do what we do with effective theory. We just ask, well, we've got these interactions. We're going to calculate things. And so we want to know how to power count things. How do you decide which contributions are large and which ones are small? And so I'm just going to go through that exercise. And I'm going to, for simplicity, assume there's only one light scale, which I'll call it H. And it'll be the scale of the derivatives of the background fields. It'll be the scale of any momenta if you're scattering particles. I'm just assuming it's all the same scale, because then I get to make a dimensional argument. And it's more complicated if there's more than one light scale, but it's not going to change what I'm going to conclude. So let's calculate some correlation function with the E external lines. And then we'll imagine looking at the contribution of a graph built from these interactions, which has L loops and Vn vertices, where n is the label of the various kinds of vertices you get from these various interactions. D sub n is the number of derivatives in any one vertex, and so on. H will be my low energy scale. And if I'm doing cosmology, then say I've got translation variance, which I don't need to have, but if I do have it, I'll assume that any momenta are also the same size as the background curvatures, so that would be appropriate at horizon exit, say, in cosmology. So I've got one scale H at low energies and all these other scales. And so now all I do is I go through, take the Feynman graph, read off where all these scales in the Lagrangian appear just from the Feynman rules. And then on dimensional grounds, the rest of the dimensions of the answer are coming from H, essentially. And that's what would have happened explicitly if we dimensionally regularize all the divergences. So that gives you an expression like this, where if I've got E, that the first two terms in this expression just depend on E, and so those are not changing for different graphs for a fixed number of external lines, but it's the rest of the terms that are the ones that are informative, and they're telling you why you have to do derivative expansion. In particular, you're supposed to notice that, except for the very last term, H is always in the numerator. And so, in particular, the term here involving the number of loops shows you that each loop, which is effectively the H-bar expansion, and which is the thing that's controlling the semi-classical expansion, what's controlling it, the small thing that makes the semi-classical expansion good, is H over a 4 pi m Planck. So that has to be small if you're doing semi-classical methods. And if you don't think you're doing a derivative expansion, the burden is on you to justify why semi-classical methods are a good approximation. But in almost all applications, in practice, people are effectively using this in the background as the reason why semi-classical methods are well justified. These terms all involve only interactions with more than four or more derivatives. So that's curvature squared and higher. And so every time you use any interactions from them, you're punished in addition to the loops by more factors of h over m Planck. And sometimes it's just h over this small mass, which was the thing in front of the curvature cube terms. But you never completely win because there's always an h over m Planck that comes along. So I have never figured out a way to take advantage of the fact that the curvature cubes could be suppressed by the electron mass rather than the Planck mass, because the prefactors of h over m Planck always seem to be too strong. But in principle, they're there. The last ones are the dangerous ones, because that's the only place where h is in the denominator. And those are the ones coming from the scalar potential with no derivatives. And so you see that generically, if v had been large, then it completely is undermining the derivative expansion. And so it's undermining the semi-classical approximation. But you get away with it if you happen to have chosen v small enough that it's of the order of h squared m Planck squared, or v to the fourth is h squared m Planck squared, which is true in cosmology. If you ask what the Hubble scale would have been if I chose a potential of size v to the fourth, it would have been v squared over m Planck. And so in cosmology, typically, these factors are 1, but they're only 1 because you've made v small for some reason. So the question is, why is v small? Now, the two things I want to emphasize are there's two things that were not appearing here. There's no penalty for fields being large. Nothing in this story required those functions to be simple polynomials of phi. And there's no penalty for two derivative terms. So this is why in general relativity, there's the nonlinearity of gravity can't be neglected at low, just because you're at low energies. But that also says that for the scalars, it's the two derivative terms you expect to compete with gravity at low energies because they scale the same way, and they'll have the same strength generically if the decay constant is m Planck. So that's, if you had to kind of bet what it is, if you see something in a test of gravity that's not general relativity, then the betting man's guess would be that we're probably seeing two derivative terms involving other fields, because those are the ones that want to compete at low energies. It could be a potential, but the potential you're kind of always trying to suppress. So it's always dangerous because it wants to be big because it's got the fewest derivatives. But once you've made it small enough to do the semi-classical story, then it's competing with the two derivative terms. So that's the good news. That's what it gives you something to think about what we should be looking at. But now the bad news is, if you happen to have made the choice, as the Euclid people did, that we're only going to look at one scalar, the interactions involving two derivatives for a scalar are controlled by this target space metric G. And in particular, if the target space is flat, there's no physics there, because you can always do a field redefinition to get rid of those two derivative interactions. And in particular, all one-dimensional manifolds are flat. So if you have only one scalar field, you never have two derivative interactions. So an unfortunate byproduct of the restriction to single fields is there are no two derivative interactions that are not general relativity. And that is why historically it's been very hard for people to have effective interactions that are visible in things like gravitational waves. If you have a Horn-Dicke model with more derivatives, you have to have the higher derivatives compete with the two derivatives. And so you're really making the whole derivative expansion start to be suspicious. And so it's kind of in retrospect easy to see why that was it's a hard row to hoe. But I think that's just an artifact of this unfortunate choice that we've thrown away the two derivative interactions. And so the message of this part of the talk is, it's not very often you have virgin territory, and it's not completely virgin. Some people have thought about some multiple two derivative multiple scalar models, but those are comparatively unexplored because of this choice that many people made in the gravity community, and they're the best motivated, I think. And so they're certainly worth trying hard to explore. And much of what I'm going to tell you in the rest of the talk is an example of a way of efforts that are exploring these kinds of interactions. So I'm going to switch from this to talking more about so that's all very nice, but why is the potential small? And so there should be a story as to why. It'd be nice to have an explanation for why that scale V was small, and that's going to set me up for the second part of the talk, which is about the approximate symmetries and accidental consequences of string theory. But it's basically what falls into the category of the cosmological constant problem, which I would prefer to call the dark energy opportunity, because I think most people agree that it's kind of it's an unusual thing that phenomenology at low energies, in this case cosmology, is using features that are not easy to get at low energies, and that is kind of an opportunity. That means that if you find something, you're learning something about high energies when you're doing measurements at low energies. And I think everybody would agree with that. And the problem has been that there have been no examples of things which are convincing embeddings of good cosmology into microscopic theories in a way that would have emerged in an effective field theory like this. And so I think my goal in the rest of the talk is to try and find an example. I think it's given that it's hard. If you find one, it's probably the way nature works. So I'm kind of I'm hopeful that that the barriers we're looking at now don't look like they're insurmountable, and so I'm kind of probably more optimistic than most are. And this is kind of why. The rest of the talk is telling you why I'm more optimistic that there might be ways to thread this rarity of what you like in cosmology coming from low energy physics. As a low energy limit of high energy physics. That might be a natural place for questions if there's any other questions about that first part. But if not, I'll just press on here. So now I'd like to talk about, so what can you say from high energies robustly, just in the way that you would have done in a general effective field theory approach to understanding low energies and in string theory. I'm going to take string theory as the of the ultraviolet gravity, not because I'm a string theorist, but just because that's the one framework which is precise enough you can ask all these questions in a very concrete way. And if you have another theory, I'm happy to ask the questions there too. So you can ask anyway in string theory what things seem to be common at low energies, and kind of there's some things that are not surprising. It seems like you have multiple fields involving not very high spins that can be light. That seems like that's fairly easy to do. There might be extra dimensions. It doesn't have to be 4. That's also very easy to do. But in particular, there are approximate symmetries. Some of them are axion symmetries, often being inherited from fields in higher dimensions, form fields. But there's also scale invariances, which I'm going to focus on for most of the rest of the talk, which give rise to dilatons as opposed to axions. And there's often many of these symmetries. And so having one is kind of the exception rather than the rule. Supersymmetry is generic, but it's typically broken. And we know that it has to be broken in the particle physics sector. But I want to argue that the supersymmetry together with the scale invariances has an interesting, they combine in an interesting way. All right, so let's do that. So let's start with the supersymmetry, because the first thing is so why talk about supersymmetry since we know it's not there? And I'm interested in very low energies. If it's not there at the weak scale when you're looking at it in colliders, then why are we even talking about it for even lower energies like cosmology? So what's generic in string theories, or actually any supergravity, is if you break supersymmetry, as we know we must, the splitting in any one multiplet is kind of generically proportional to the size, the order parameter that breaks supersymmetry, which I'm calling F here. But it also involves the coupling strength between the multiplet of interest and the field who got the expectation value F. So I've drawn 2 sectors here. These are supposed to be energy levels. The standard model sector is on the left, and it's split by more than the gravity sector. And I've done that because that's actually very common in string vacua. And that's because gravity typically is the weakest coupled theory interaction or particle in the problem at low energies. And because it couples the weakest, it's kind of generically the split the least by supersymmetry. You can arrange to not do this. And so most of the popular ways of breaking supersymmetry have been designed to try and make the gravity sector not be split by less than everything else, but it's not the generic thing. This is the generic thing. And you can imagine now if your ultraviolet cutoff is here, it would not be a stretch to have a non-supersymmetric matter coupled to very supersymmetric gravity, depending on exactly what these splittings are. So that's, and the nice thing, this observation was made actually in the 80s, I can remember. But the nice thing about being alive now is that the effective theories of this type of non-supersymmetric matter coupled to supergravity it's now known how to write them down in a systematic way. So you can actually be very systematic in describing what these interactions look like. And I'm not going to actually talk about that formalism at all, but that's what I'm going to be using behind the slides is this formalism. And so I'm going to be describing the implications of that formalism. And you might think, well, that's all very nice, you've got a formalism, but if it's true that the particle physics sector isn't supersymmetric, why do I care if this gravity sector is supersymmetric for questions like the dark energy problem? That's about the particle physics and how it gravitates. And so here's the point, I think, of that of the possibility that the gravity sector could be supersymmetric. That is that the auxiliary fields that appear with the supersymmetry, they give structure to the potential in a way. For instance, it makes some terms positive because it's a square of an auxiliary field. And once things are positive, then relaxation mechanisms can be built around them because they're naturally minimized at 0. And there's a precedent for having non-propagating fields like auxiliary fields actually change naturalness arguments and change effective field theories. The quantum Hall effect is a classic example of this. There's lots of non-propagating fields. In that case, what they're there for is to tell you how if you had an interesting topology in your system, how the low energy degrees of freedom interact with it. And so there are fields that you wouldn't have included if you had just been counting the propagating degrees of freedom, but they're really in the low energy theory because they're bringing topological information, it turns out. And it turns out that naturalness arguments change in the presence of non-propagating fields. And it's also true if you look at dual, even if it's propagating fields, dual ways of writing fields like scalar fields versus asymmetric tensors, the naturalness properties that come with those dual ways of thinking about it can be different. And so if you're focused on naturalness questions in particular, it's tempting to say, well, if I've got equivalent ways of thinking about it, I'll think about it the easy way and think about the scalars. And that's normally a good argument with the exception of naturalness arguments. And this topological non-propagating fields and auxiliary fields are actually not different from each other. Since the 2015, we've known that every single auxiliary field you get in a low energy string theory that in the 4-dimensional supergravity, they're all topological fields in the higher dimensions, it turns out. And so I think probably this is one of the unexplored directions that hasn't been thought through carefully enough yet. And part of why I'm optimistic is that the implications of these non-propagating auxiliary fields in the structure of the potential and how you can use that to make the potentials small hasn't been explored very systematically yet, I think. So now I want to switch to, so that's kind of the supersymmetry story, and it's going to come back in a second. But I want to talk about the scaling symmetries, which I've alluded to as being ones that are underappreciated. And so I want to claim that every single string vacuum you've ever seen has at least one, usually more than one, scaling symmetry of the following form. The metric scales by some constant factor. Other fields in your problem scale by other powers of that same constant factor, and the Lagrangian scales by a different power of that constant factor. So it's not a symmetry in the sense that the action's invariant, but it is a symmetry in the sense that the classical equations of motion are invariant, this kind of a symmetry. The reason these symmetries are so generic is actually easy to say. In string theory, you don't have any small parameters. All you have are fields. So if you're doing the low energy expansion, or if you're doing the string weak coupling expansion, you're really always expanding in the fields. So your Lagrangian at low energies comes to you as a sum over these fields, like inside the box there, the sum. And so now it's not a surprise if I scale those fields in some specific way that any one term in that sum scales in a specific way. And in particular, the first term scales in a specific way. And so what happens is, if you go to 11-dimensional supergravity where the only approximation is the low energy approximation, there's one scaling symmetry, and it's easy to identify it amongst the light fields. In 10-dimensional supergravities, there's two because you're doing the low energy expansion and you're also doing the weak coupling expansion and so on. And you can go through the list of all the various vacua and you can identify these scaling symmetries. They're completely generic to supergravities in higher dimensions because of this string underlying argument. Now, what's special about these symmetries, the reason I'm kind of focusing on them is that if you get a potential which scales in this way, then the things in the boxes are just identities you derive by differentiating that scaling relation and various times and then setting lambda to 1. The first box says that if you have a place which is scale invariant, or sorry, the second box says that if you have a scale invariant point where phi is 0, so the fields, all the fields that are not 0 don't scale, then it's always true that that's a stationary point of the potential. That's not a surprise. If you have a symmetry of a potential, the invariant point is always a stationary point. And that's true for the Mexican hat, and it's true in lots of examples. The interesting one is the first one. It says if you have a stationary point of potential, it's always a place where the potential vanishes. And what's happening there is that if you have any point where you've got a stationary point and you've broken the scale invariance, if you do this for the scale invariant point, it's not a surprise that it's potential 0 there because there's no scales. But if I've got some expectation values of fields which are non-zero, so I've spontaneously broken the scale invariance, what's happening, transformations relate the different values of those fields. And because it's a symmetry, they're all degenerate in potential, so they have the same value. But unlike the Mexican hat, where the symmetry broken directions are disjoint from the top of the hat, which is a symmetric point, for scale invariance, it's not a phase, it's a real number. The scale invariant point is just one of the points on that line. So everybody's anchored to the scale invariant point, and so has to be at 0. And so because of that, even if you spontaneously break scale invariance, it still protects the potential and makes it want to be small. It makes it want to be 0 if scale invariance is true in the sense that I'm describing here. And people made that observation basically in the 80s and tried to build models where you broke scale invariance a little bit to try and exploit this potential being small. And then Weinberg shot it down within 2 years with a no-go argument, which I can come back to if people are interested. But the essence of the story there is that everyone knows that scale invariance is not a symmetry. It's not just spontaneously broken. It's just not. It's just approximate. It's what we're talking about here is not a symmetry of the action. It's a symmetry of the classical equations of motion. So the question is always about how big are the scale breaking effects and why don't they generate a potential which is bigger than the one that this argument is suggesting. And this is where I think the interplay of supersymmetry and the scale invariance is better than the sum of its parts. So this is leading to the mechanism I told you for how there's a general mechanism for suppressing a potential, corrections to a potential that is suggested by these arguments that I'm about to describe. So what I want to do is I want to re-ask what scale invariance looks like in a supergravity. I want to, because it's the interplay between supersymmetry and scale invariance that I want to exploit for this mechanism. So the box here just shows you that that you can write down. The details of the supergravity don't matter. It's just I'm just reminding you that a supergravity in 4 dimensions is specified by a Kähler function k, a superpotential w, and a gauge kinetic function f at the 2 derivative level. And then there's formulas like in the second box for what the component action is in terms of those functions. And the main thing I'm telling you that this for is 2 things. One thing is the metric. When we get to the Einstein, when we write down the Einstein term, when you take these expressions, you don't arrive in the Einstein frame, and so you have to go to the Einstein frame. And the frame change you have to do is given by k. So if I tell you k, I've told you what the scale, what this redefinition is, and that will be important because that's going to tell us that the scalars we're going to find later on are Brans-Dicke scalars later on. So I just want to flag that now that the standard rules for supergravity include a Weyl rescaling to get to the Einstein frame. Second thing is, if I tell you how things scale in a scale invariant way, this whole Lagrangian is supposed to scale, but the rule for k will be that e to the minus k over 3 should scale, not that k should scale because of the way it appears in the Lagrangian. So let's imagine that we have a scale invariant theory where e to the minus k over 3 scales to a multiple of itself as the various fields scale. So I've got a homogeneous degree 1 function in e to the minus k over 3. If I differentiate that multiple times, I can derive this the identity below here, in the first box in the second line, where kij bar is the inverse metric to the second derivative of k with respect to z and z bar. That identity is significant. That's what we call a no-scale model. And you can kind of see from the bottom box, the potential energy is whenever that's true. If the fields involved don't appear in the superpotential, then the potential energy exactly vanishes along any place in field space satisfying that identity. And a supersymmetry turns out to be broken there. So it's not supersymmetry that's making it flat. It's a supersymmetry breaking flat direction. And those were kind of remarkable when they were found, and they were found back in the 80s, and they're called no-scale models. Now, the interesting thing is that that scale invariance is necessary. It's sufficient, but it's not necessary for the flatness of the potential. So for example, this formula here is also a no-scale model. It turns out it satisfies that same identity for an arbitrary function f of other fields z and z star. So the first term is scale invariant. It's homogeneous degree 1. But the second term doesn't. It's still true that this would be a no-scale, exactly a flat potential, even though it's not scale invariant. So it turns out that there's kind of a nested sequence of things that have flat potentials, which were analyzed back in the 80s. And the mechanism I'm going to tell you about is based on the fact that you could start in the D sector here. It's scale invariant, and so it's got a flat potential. corrections will break the scale invariance, but they need not make the potential, lift the flat direction of the potential if they leave you in these no-scale models. And that's what this mechanism is going to do. There's a class of corrections which can break scale invariance and not change the potential, even though they do break the scale invariance. And that's the sense in which supersymmetry is helping protect the potential when it's combined with scale invariance. There's a side story which I won't emphasize, but in passing, I'll mention that the difficulty in getting de Sitter space in string theory is, I think, related to this, that everybody who's trying to find de Sitter space is always they're fixing moduli, and they use the superpotential to do it. And because of that, the fields like to be at supersymmetric places. And so you're in a regime where supersymmetry is broken by less than the scale invariance, and that tends to drive you to anti-de Sitter space. When you perturb around that, it's hard to get to de Sitter space. But if you try and find solutions, which have been done recently, not in string theory, but in supergravity, where you deliberately make the scale invariance breaking less than the supersymmetry breaking, then what happens is you're perturbing around zero, because scale invariance likes zero cosmological constant, and then going up and down is equally easy. And so I suspect that there's interesting things to say about de Sitter space, not dark energy, but for, say, inflation in string theory, exploiting these symmetries too, but I'll pass on that right now. Now, here's the mechanism I was telling you about. So let's suppose we have a field tau, and it's large. So everything's coming to us as a series in 1 over tau. So this is one of our expansion fields in string theory, let's say. Might be the volume. There's lots of examples like this in string theory. And let's imagine that e to the minus k over 3 starts off linear in tau, so it's scale invariant, and so it has this no-scale structure. But now we look at the corrections to it, and now the second term, which is down by 1 over tau, has no taus in it, because the 1 over tau cancels the leading tau. And then the third term has the 1 over tau squared times tau, which that's a total of 1 over tau. Now, what's important about this is that the first term was scale invariant, and so that's kind of had a flat potential. And now, but now we're looking at the corrections to it when we look at the series in 1 over tau. The second term is still no scale. I told you that for any function, the A, B, and C can be functions of all the other fields as long as they're not scaling. And if B is an arbitrary function, as long as it doesn't depend on tau, that's still a no-scale model and has exactly flat potential, and that breaks supersymmetry. It's only at this point that the potential breaks. And so this mechanism is a mechanism that allows you to break the flatness of the potential at 1 order perturbation theory higher than you thought you would, generically based on just the scale invariance alone. That's what supersymmetry is doing when it's combined with the scale invariance. And these are the people that found it. They were working in a particular context in string theory, which doesn't really matter. But it's that's essentially what was going on. Now I see I'm getting kind of close to time, and so I'm going to be telegraphic in this last part. And this is about the specific model. So the model I'm going to describe, the yoga models, just takes literally that theory I gave you with k, e to the k over 3 is a series in tau, and I'm going to try and make tau as big as I possibly can so that the corrections are as small as they possibly can, and see if you can make progress in the dark energy. And so I'm going to now just telegraphically tell you where that goes, but I'm just turning the crank with the supergravity with the rules that I gave you before. And of course, the field tau is there, but it comes with an axion because it's coming to you as it's in a supergravity. And so at low energies, you get something like this, where there's a kinetic energy for tau, and that kinetic term is dictated by that leading term of e to the minus k over 3 being tau. And then there's a potential, which I'll say more about, and there's couplings to matter. And the main thing to know about the couplings to matter is they involve this Weyl rescaling I alluded to. And that's a specific function of tau because of the structure of k that I'm assuming when I make this, that I use this mechanism. Now that means that in the standard model, the only thing that breaks scale invariance is the Higgs mass. So everybody who gets a mass proportional to the Higgs VEV turns out to have a mass which is proportional to 1 over root tau in Planck units. But things like the neutrino that have 2 Higgs VEVs in them can have masses that are suppressed by 2 powers of 1 over root tau. And so that actually hierarchy that works numerically. If tau happens to be 10 to the 28,
a 5D metric transform.
Sorry, could you repeat the question?
I think someone was just unmuted. I think it's fine.
Oh, I'm sorry. Okay, never mind. So just in passing, I want to say that this is actually a numerologically successful prediction. If you have M Planck and tau, and the weak scale is given by 1 over root tau, and the neutrinos are 1 over tau, that works if tau is 10 to the 28. So if I give you a story which gives you 10 to 28 for tau, independent of the cosmological constant problem, I'm going to be telling you why neutrinos are light and why the weak scale is small compared to the Planck scale. All right, so now that's all about the size of tau is all about the potential, and the potential comes to you as a series in 1 over tau, and it has this form. And what's important is that the squareds like Wx, that's an auxiliary field. So it comes to you as a square because of the supersymmetry of the gravity sector. Now, that's not small. The term that goes like 1 over tau squared, that's if the weak scale is going like 1 over root tau, that's something which goes like weak scale to the 4th. That's the thing that we're worried about in the cosmological constant problem. So there's no miracles there. But because it's a perfect square, you can imagine there's now another field in the problem. We'll call it phi, and it's a relaxation field. It wants to minimize. It appears in Wx, and it wants to minimize that. And so if all we had was the first term, it would make it 0. But we also have the second term, so it doesn't make it quite 0. It makes Wx instead over order 1 over tau. But once it makes it order 1 over tau, every term there is order 1 over tau to the 4th. So what you're led to is a potential which has this form, and it depends on the logarithm of tau, the coefficient of 1 over tau to the 4th, because all those coefficients can depend on logarithms of mass ratios, and all the masses have taus in them. So if I have, say, neutrinos divided by other particles, then the log of a mass ratio has a log of tau in it. So it's also true that that could have a log tau dependence. Now, the reason that's significant is that it's very easy to make a function. I'll give you a quadratic function of log tau, and I'll put no coefficients in it that are bigger than 60. And I can very easily make the potential have a minimum where tau is 10 to the 28, because it's a function of log tau, and so this is the kind of potentials you get. And so this kind of a structure of a potential is something which is very, very easy to arrange without putting in very small numbers in this kind of a relaxation framework. What's nice about that 1 over tau to the 4th answer is that if you think of the standard model scale being 1 over root tau, well, I can see that that's my time, so I'm gonna be very telegraphic in the last few slides here, and then the things that I don't say, you'll have my slides, and so you can read them if you're interested. But I'll just finish this thought, and I'll cut to the conclusions because I know that we're pushing the time. All right, so the numerology here is interesting because it says that the potential at the minimum wants to be of the order of tau to the 1 over tau to the 4th, which is the standard model scale squared divided by m Planck to the 4th power. And that's numerologically, that's kind of the scaling with the weak scale that the vacuum energy is observed to have. Now, that's not quite a fair comparison because I should be comparing to the supersymmetry breaking scale in this picture, because that's the vacuum energy that wants to be the biggest. And that might not be standard model particles.
So one quick question. How you can stabilize, let's say, trans-Planckian tau? Because if it's trans-Planckian, if we think in the terms of particles, it means like it's in principle could collapse in black hole, right?
No, it's only danger if you have a lot of energy, and there's nothing in large tau which has a lot of energy necessarily.
Well, why not? Because it will have large kinetic energy at least, right? Because
Well, that'll depend on how you set the universe up.
So the same order, let's say.
So it's true you can't have derivatives that are large, but the value of tau can be anything. There's no energy cost in having large tau in the potential I showed you. It actually, the larger tau is, the more it gets to 0. So that large tau is actually a place that the low energy theory loves to be in. But it's true you can't have gradients that are at the Planck scale, but that's always true in any effective theory. So I won't have gradients that are large. They'll be of the order of the Hubble scale in the examples I'm going to show you.
Okay. But I still have a question about this. Sure.
Okay, well, we can come back to it at the end maybe. So the bottom line is F star F is what you generically would have thought the vacuum energy would be when you break supersymmetry. And what this answer is showing you is that the answer is suppressed compared to that by 1 over tau. I told you there's going to be a suppression by 1 order of magnitude, 1 order of perturbation theory more than you thought. And there it is. It turns out there's a for free suppression by 1 over log tau to the 5th power that is not designed in. It just happens to come out when you minimize things. And if you just take those numbers out of the box, that takes you to 10 to the minus 91 m Planck to the 4th, which is not 10 to the minus 120, which is where we have to be, but it's way better than anybody else. But anytime you're below 10 to the minus 80 m Planck to the 4th, you've got the problem that you're mediating long-range forces, and that change makes the focus more on tests of gravity. So what I'll do here is I'll kind of, this is just a summary of the things that happen with this. If you try to make a cosmology of these fields, some interesting things happen. So that in particular could have relevance for the Hubble problem. And I'll show you one slide about that, and then I'll go to the conclusions. And there's other things here that are nice things, which you're interested in the model, I could talk more about. And some of these things are being rediscovered by the swampland people who are rediscovering large dimensions. So I'm going to say the one thing here about the Hubble problem and why the story I'm telling you could be relevant to that. It's not known if it is relevant, but it's kind of a surprising that it could be. given that it wasn't designed to be. So the starting point here is if you've read this Hubble Olympics paper, it's a paper that ranks ways you could change the fit to try and fix the Hubble problem if you're trying to do that. And the one that got the gold medal here is the one that's circled. And that, it turns out, if you were to vary the electron mass by about 8%, I think it is, at recombination, and if you also vary the baryon and the dark matter abundance by that same 8%, then what happens is that you don't change the spectrum of all the equilibrium physics in the CMB. You change the small non-equilibrium effects, but not the equilibrium effects. But you move the recombination surface back because you've changed the electron mass. And so the recombination temperature is a little bit different. And because of that moving it back, you change the Hubble scale that you get out of the CMB. And then that turns out to be a very good fit to the CMB. The BAO doesn't quite work as well, but a wrinkle on that is you could fix that in a variety of ways. One of which is you could have a small spatial curvature, and there's a variety of options that they look at, which I'm not going to really explore much. I'm just going to start with the observation that if you change all the masses, if you change the masses of baryons, dark matter, and the electron all at the same way at recombination, that could do a good thing for the Hubble scale. And the reason I'm emphasizing that is that if you take these, the theory I'm describing you, and look at a typical evolution of a field, this is what you get. So I'm showing you the evolution of the log of tau. It's a dilaton. And I've got nucleosynthesis at the left, and I've got now at the right. And this is not something which was designed to happen. I started off at nucleosynthesis with the value of tau exactly what it is now, so that all the masses at nucleosynthesis are the same as they are now, and they're not changing. And what happens is that very generically, this thing does an excursion, because what happens is it's a very scale invariant problem. The field gets into a tracker solution. You go past the matter radiation equality, and the trackers change, and that kicks it out of the tracker solution into a new one, and does this big excursion, which is very easy to be at the 10% level. And then it settles down in the potential that I described, and then it becomes the dark energy from then on. And so it would be very plausible in this kind of a picture to have all the masses, and it wouldn't just be the electron, it would be everybody, because the dilaton's changing. So everybody in the standard model changes. And as long as the dark matter changes in the same way, all those requirements of the dark matter and the baryon density changing the same way as electron mass are for free, being satisfied, because all the masses are changing the same way. And that could very well be progress. That is actually very suggestive of the best solutions in these Hubble Olympics. So now, the thing that we need to know, the reason I'm not claiming there's a solution here is that this excursion is happening where you can measure a lot of things. Structure formation is happening there, and then you have to settle down into this potential, the redshifts of a few. If this thing hasn't settled down, then the electron mass is changing, and so spectral lines could start to change. And so there's a lot of things to check here. And this is where having the technology of multiple fields and how that propagates through gravitational fluctuations is needed, and it's missing because the focus has been on single field models. So let me just, there's a story here about birefringence if you're interested, but and there's a story about screening, which I could also, if you're interested. But what I'm going to go to is the conclusions. I had 3 conclusions. The first 2 are basically the observation that it's a remarkable opportunity that the success of cosmology relies on things that are hard to get but not impossible to get from high energy physics. So stuff that is not decoupling is important in cosmology. Things like small vacuum energies and light scalar masses. And they're linked to each other. If you have small vacuum energies, that can very generically give you light scalar masses. So I think it's very useful to think about the implications of UV physics for long distance physics, but in a way which I think is completely different in philosophy from the swampland program, because this is standard vanilla symmetries, robust predictions at low energies, comes from a generic effective field theory program, and there's no assertion that there's some special feature of the high energy physics that's showing itself through things like the difficulty getting de Sitter space. I think that's, and so because of that, you're not driven into conjecture physics, and so I think it's a much more constructive way to think about low energy physics, and it's very largely unexplored for whatever reasons. The physics you get is very rich because there's likely many scalars there at once. And once you've made the vacuum energy small, they like to be small. And there's a good reason to think that the vacuum energy could be small, but the things that are still not understood are the phenomenology of the scalars. There's these you can easily make the vacuum energy small enough that these scalars are playing a role in the solar system in tests of gravity. I didn't emphasize it along the way, but that Weyl rescaling that you do says that the dilaton couples to gravity in a Brans-Dicke way, where the Brans-Dicke coupling is 1/√6, whereas the bounds on the Brans-Dicke coupling are more like 10 to minus 3. And so there's an issue there of how do you evade those tests. But in this class of models, the physics, the smallness of the potential is a given. And now the question is, can you model build around the problems of the phenomenology of the light scalars? And whether that's possible or not is really open. And I hope you'll join in. There's much to be done. So thank you for your time. Sorry for running over a little bit, but
thank you very much. Thanks, Cliff. Yeah, we had a few questions already. If anyone has something really burning they want to ask, please go ahead now. I think we can stick around for as long as people are willing to stick around, I guess. But yeah, who would anyone like to go first? Archil? Oh, okay. I thought Archil was going to ask something because he
I think there are people who want to ask the question before me, so maybe we can.
Well, yeah. I mean, I had a question, but it's really basically on just this sort of the stuff you had towards the end that you skipped over. I'm actually quite curious about this birefringence story. Is this
yes,
sort of is this just some like the usual like axion FF dual interaction or something that this is a consequence of, or is there something
it's
else
relying on that.
going on?
It's relying on that. I can give you like a 2-line thing. It's relying on that, but it's the difference between this and the Axiverse story is that the Axiverse story is all about you have to have a mass in the sweet spot, and so you're arranging for this scalar to be interacting with the potential at just the right time that you're seeing it. And what I'm going to show you is in that same cosmology that was doing the nice thing for the Hubble story. In that whole cosmology, the axion was basically massless, so you didn't have to adjust any mass to make it work. And the thing I want you to see is just the plot of this one here. So it's so what this is this is the plot of the various components of the energy density as a function of time. And you can kind of see that the I don't know if you can see my mouse here.
Yeah.
Yeah. So the axion is this dash dot line. And what's happening is that these fields they're all kind of straight lines because on a log plot because they're all tracker solutions. So they all go into these power law solutions. And then there's transitions as things like radiation matter happen. The green line is the dilaton kinetic energy. And you kind of see that it gets snagged at the potential here. So it does some interesting things. But basically, if you follow the axion, the dark matter is this blue dashed line. And that what happens is that the axion starts to track the dark matter. So what I've shown in the table in the bottom here is if you look at right now what the fraction is in everybody, it's given by this. And in particular, you can see that that there's about half axion and half dark matter. Like the non-relativistic matter part of the story, the dark matter we stuck in is actually only half of what's there because the axion just tracks it. And so that means that you have an axion, homogeneous axion density, which is everywhere, and it doesn't really rely on tuning a mass to be in the right place. And so if you now ask, if this thing is coupling to the photons in any way at all, if you ask what's the integrated angle that you would see in birefringence, it turns out to be this, and it's super easy to get that to be order 1 because it's just there the whole time. And so it's so there's lots of things that have to happen in order for this to be really a model of birefringence, because in the story that I didn't talk about screening, the one screening mechanism that we have involves the potential for the axion. And so for that one mechanism, you can evade solar system tests, it seems, but this would not be the cosmology for that system. And so what's not known, this is assuming that the dilaton is coupling in an unsuppressed way in cosmology, which would be actually plausible because the screening is about inhomogeneous sources. And so homogeneous sources actually wouldn't be screened. And so this is kind of a plausible thing, but it evades the mechanism for generating the axion is none of the standard ones, because what's really happening is it's the dilaton axion kinetic terms. The time evolution of the dilaton is then driving the axion and winding it up, and so you're getting it in a completely unstandard way. And so because of that, all the details of how things depend on the parameters change.
Yeah, Murray, Archil, you can go next. Oh, you're muted still. You're muted, Archil.
Thank you, Cliff, for a very interesting talk. I just had this question about the dilaton. You mentioned that one of the 6 and presumably about the screening mechanism. So you mentioned this
Yeah.
coupling 1/6, which is a conformal coupling. Presumably that has the corrections, the just radiative corrections, so the deviation from 1/6. And in any way, I mean, the dilaton should couple also to, trace of energy momentum tensors through the anomaly. So I don't quite understand how you can screen, the 1/r² kind of fifth force things, the tests, for example, in torsion balance experiments or something like that.
Not obvious. So I can tell you the story here if you like. Again, I'll try and make it telegraphic so I don't take up too much time. But it's not an obvious story. But I should say that the 1/6 is not the conformal coupling you're talking about. It's not the coefficient of phi squared r. This is the Brans-Dicke coupling. If you look at the Weyl rescaling of the metric, it's an exponential of chi, which is what makes it Brans-Dicke, and the coefficient there is 1/. That's the thing that's 1/√6. So it's omega there is the Brans-Dicke parameter that people normally talk about, and so the g I'm talking about is the one that's defined in omega, that's the rescaling function, and that's the thing.
Anyway, dilaton couples to matter quite strongly.
Definitely, and the bound is basically 10⁻³ or something like that for g, and so the first thing you can't use the standard screening mechanisms that people all use because those are all single field things involving the balancing of higher derivatives, lower derivatives, and so it's very difficult to make it work in this context. So we set out to find a screening mechanism that involves just the two derivative interactions. And here's the best we found, and there may be better ones. So the idea is, so this is all I'm doing here is I'm writing the Lagrangian out. So phi is what I called chi. It's just the dilaton, the canonical dilaton. And then the axion is the axion, and then w² is the thing that when I wrote it before, I had d tau squared over tau squared and dA squared over tau squared. So think of if it canonically normalized tau, w is basically an exponential of phi in the way that I would have given it in the rest of the talk. But for the purposes of looking for screening, let's just take that as a function and just ask, what can you do? And now the things I'm going to need in order to have this mechanism work is I'm going to need a potential for the axion. And it's going to be suppressed the same way that the dark energy is suppressed, the axion potential will be suppressed. So I'm going to imagine it's smaller than it would have been for the QCD axion. And I'm going to have coupling to matter. And so I'm going to have a potential U of A, which is a different function. And the one thing I'm going to use about those potentials is true of this QCD potentials, but I'm going to not use, I'm going to assume the sizes of everything is smaller than it would have been in QCD. But the thing I'm going to use is that the U of A and the V of A have different minima. So that means, and I'm going to assume that V of A is small enough that in matter, ordinary matter, the matter-dependent term, rho m times U of A, is the big potential. And so the axion wants to minimize U inside matter, and it wants to minimize V outside matter. That's the thing that I need to have happen. And for the QCD axion, that would happen for nuclear matter, but it wouldn't happen for ordinary matter. But I'm going to imagine everything smaller. So now if you do that, what happens is that the axion always has to have a gradient it wants to be in the vacuum outside and the vacuum inside. So near the surface is always a gradient. And as soon as you have a gradient, then the other field can see it through the derivative interaction. And so what happens is if you take the limit, this is just for to make it simple to see what happens. If it happened to be very, very sharp gradient, then what the dilaton essentially sees is like a delta function at the surface of the star. And so what happens is that there's a jump condition for the dilaton as it comes through this axion gradient of the form of the bottom of this page here. And so that is very easy to make it go down. So what happens is that inside the star, the dilaton couples just like a Brans-Dicke scalar. It's got a big gradient, but then the gradient of the dilaton jumps as you leave the star as it goes through the axion gradient. And the thing you see in the solution outside that you're testing is sensitive to the gradient outside the star, and that jump is the suppression that's giving it a screening. And from what I've told you so far, there's no reason why that jump has to be large. So there's no reason why it'd be super small. So the missing piece now is, when you solve for the dilaton inside the star, the integration constant of the value of the dilaton at the origin of the sun is something which you normally would have just chosen. You integrate it out and you use it to match onto the field at infinity. And if you have a shift symmetric dilaton, that would be perfectly reasonable. But what happens now is that this W of phi is making the energy of the star care about the value of the dilaton. So it's breaking the shift symmetry. So if you ask what value of the energy minimizes if I let the value of the additive constant in the dilaton adjust to minimize the energy and ask what's it do, what it likes to do is it likes to turn off the derivative of the dilaton outside the star, because the energy of the dilaton, which is this gradient, this 1/r term going out to infinity, that's a big piece of the energy. And so if it can minimize that, it actually loves to do it. So the adjustment mechanism is that field is adjusting to let to minimize the energy of the star, and that drives down the coupling of the dilaton. But the problem that means is that the value of the field at infinity is now predicted, because it's a function now of the mass and the radius of the star. So if I do this for the Earth and for the Sun and for all other things, they're going to give me different values at infinity, and the field has to somehow adjust. And so there's a frustration thing that goes on, is that the field has to ask, is it energetically preferable to minimize the coupling to the star or the Earth, or have a gradient at infinity which makes these fields meet one another at infinity? And what happens in that trade-off is that the source which has the largest value of surface gravity, gm over r squared, wins. So in the solar system, the sun wins. So the scalar likes to make the sun have the smallest coupling possible. And then the Earth does the best it can. And then there's a gradient which is set by the astronomical unit, essentially, which is adjusting. And as the Earth moves, it's an adjusting thing. So there's a lot of phenomenology to do with the failure of the screening to be perfect, and the Earth and the time dependence of it, and all the masses are functions of this field, and we just get away with it just barely, because the effects and the changes of the mass of masses of particles on the Earth, let's say, they're suppressed by gm over r for the Earth, which is like 10 to the minus 10, and then they're also suppressed by this Brans-Dicke coupling, which has been designed now to be 10 to the minus 5. But so that puts them at the kind of 10 to the minus 15 level, and atomic clock measurements of masses are kind of in the 10 to the minus 16, 17 level. And so the thing is, you're in the level now where this kind of a model could be maybe detectable for atomic clocks, and that part of it we're still thinking through. The danger, there's another story to do with the decay constant, but there's a whole bunch of phenomenology here, which is it shouldn't have worked, but it seems like there's a window where it can work, is basically the message.
Yeah, thank you very much. I think I have to read your papers more carefully. I still don't quite understand. I was talking in a smaller distance, in a torsion balance experiments, for example. If that works, yeah. Anyway, thank you.
Right. I think those are safe. I think those ones were safe just because the coupling's weak enough.
Okay.
It looked like a change in Newton's constant, because it's not changing the inverse square law, and so I think those ones were safe. The one that's dangerous is Brans-Dicke models. They're normally very good with equivalence principle tests, but once you start screening them, that starts to fail. And so that I forget the name of the satellite that they put up. The tests of equivalence principle there, those are also on the edge, but they work. So there's a lot of things that could go wrong, but it seems like it works. And this may not be the best mechanism. It's the first one we found that seems like it works. So.
Yeah, maybe I'll allow Otto. Did you want to your question again?
Yeah. Thank you. So I would like to ask how you produce, let's say, Transplanckian fields, because in usual pictures we cannot get there where effective theory breaks down. So
see, that's actually wrong.
In your case, it was y far from the Planck scale, right? So how you stabilize, let's say, potential and so on?
So the stabilization of the potential is what I showed, but the basic the mechanism we're using for Transplanckian fields is one that many string vacua use. There's absolutely nothing in effective theory which says that you can't have Transplanckian fields, and the classic example of that is the radius of any large dimension, because if you canonically normalize the radius, your potential comes to you as a series in 1 over r normally for a large radius. And if you canonically normalize the radius from the Einstein term in a compactification, it's the logarithm of the radius, which is the canonical variable. So those are coming to you as potentials that are exponentials in the fields. And the regime you trust is when the radius is large, and that's the regime where the field, so the radius is the exponential of the field, canonical field, divided by m Planck, essentially. So the regime you trust the thing I forgot to say is the radius in string units, for example, is e to the phi over m Planck. So you trust the expansion of the field theory when the radius is large compared to the string scale, and that's exactly the Transplanckian regime, where the fields are bigger than the Planck scale. And the bigger they are, the better it is in the effective theory. And there's no contradiction there, because the energy cost in the potential is smaller and smaller and smaller the bigger the radius is. So there's absolutely nothing in an effective theory that forbids you talking about Transplanckian fields. Normally, people say that when they're talking about inflation. And if you want to have a lot of energy for a large field, then that's a more difficult thing to do. And so
Because I would
inflationary
like
models,
to think in terms of virial. So if I have, let's say, Transplanckian, let's say wave, then the kinetic fluctuation should be same order. That's my intuition. That's why I'm asking. If
that's
you
not,
have large field, let's say, then the kinetic fluctuation should be the same order. Especially with
kinetic
coupling, which you had like 1/tau square, and then you had like 1/tau square, like tau gradient square, right?
yeah.
So,
So when you say the two things that are the same order, I'm not sure what they are. So you see, when you say kinetic fluctuation, what do you mean there?
well, like the derivatives of the same field.
Well, there's no, those often, actually, those will be often the same order, because that's the field equation will say that box phi is equal to the potential or something like that. So
Right.
but those are all
That's why I'm
large
asking,
field.
because if derivative is same order, then with the graviton it couples with a derivative, right? So
Yep.
with the graviton coupling is derivative over M Planck. And if the derivative is Transplanckian, then that coupling is not anymore weak coupling.
Well, the assumption you're making there, which is not true in these models, is you're assuming that the Transplanckian fields are giving you a lot of energy density. And that's not true in these models. In these models, when the fields are large, the potential is actually very small. And so the derivatives are also small because they're all of the Hubble size. So in that case, the large field limit is actually a low energy limit. And it's true that in inflationary models where you're trying to get a lot of energy for large fields, those are the ones where the kind of thing you're worried about happens, but not in these models. So the derivative expansion is completely under control because it's a low energy limit, the large field limit.
And then how you stabilize itself the potential that it doesn't get radiative corrections from the graviton, let's say.
So that's coming from, let me just show you the potential here. So so this potential I'm showing you here, if I just take the supersymmetric gravity and I couple it to the standard model and to this field tau, this is just what happens. And it comes to you as a series of 1/tau because the whole thing's designed to come to you as a series of 1/tau. And the thing that's non-trivial here is that the first term happens to be 1/tau squared. So the claim is that this is actually the most general thing you can write down consistent with the symmetries, because the way I got this was I took the scale invariances that was organized by the powers of 1/tau, and I took a generic gravitational coupling and I just calculated what's the most general potential, and this is what it is.
But
so the thing that
from this potential, I would say that itself tau is not active field because tau 0 is not a minimum, right? So it's the opposite. Tau minimum is like this potential actually blows up on tau equals to 0.
you're not allowed to go near tau equals 0. This whole thing has been designed in a large tau limit. So the low energy limit is large tau.
Yeah, sure. Yeah,
Yeah, sorry. It's my end. It's really going crazy. Sorry.
Okay, I think that sounds like that was not a question. It was a mic thing.
It was a faulty. It's a faulty Zoom essentially. Sorry. Yeah.
Okay, never mind. Okay. Yeah, so the story here is that the domain of validity of this theory is large tau. So you're not allowed to think of tau being 0. If any equations make tau small, then the way it was derived breaks down, and you have to have a different set of approximations. But in the large tau limit, this works fine, and it's true that generically for a random value of tau, that will not be a minimum of potential, but that actually doesn't matter. We understand the Higgs potential, even if we're not at the minimum.
Practically, you are telling me that you should consider some wave plus tau and let's say expand on that and get polynomial potential out of it. So itself,
Polynomial and what?
like you should consider tau equals some wave plus fluctuation, and for what that fluctuation you get some kind of polynomial potential. So,
yes, in the fluctuation, definitely. So when I gave you the theory,
so then that fluctuation is actually the active field, and that fluctuation will be never Transplanckian, right?
That's right. Yes.
And
So
all
in the later
couplings
thing,
then will be, let's say, cut it off in less than 1/MP.
I won't have to cut it off. It'll never go there. It doesn't go that far.
It doesn't go that far for the fluctuation. So
Right. So in this
then
cosmology,
that fluctuation is a degree of freedom, not tau, right?
no, it is tau. It's a deviation of tau from a particular value. So when I'm showing you this, this one, the x here, that's the logarithm of tau. And the minimum is at 74. You can kind of see the inset is the potential plotted as a function of chi, of x. And so this is a cosmology where you see x rolling around, and you can see it's rolling around in a region around 74, and it doesn't go very far. It doesn't in Planck. This is in Planck units. So going a significant amount would be off scale on this graph. And there's nothing in the approximation that's failing here. And only one of those points is a minimum. And you could expand around that if you want to.
And can I ask about this axion coupling as well?
Okay.
From which you started. Like there you have, okay, decay constant. Thanks for this clarification, tau. With the axion, you had decay constant with M Planck. Okay, it fits in your usual Peche Queen or two form, whatever, like they are same. But then you have potential, and that potential is either from topological susceptibility and then is protected. And then cutoff for the theory is what, like that QCD scale or whatever, or that potential is not protected and it will get radiational corrections, right? And during your talk, I understood that you are getting that potential from the tree form.
I didn't use that, but it's true that we there's a UV completion which we're coming from the form, right?
Then when this tree form has this, let's say it has the energy scale which is less than Planck. So why you should not UV complete before M Planck that theory?
You have to. So that's actually something I didn't emphasize, but these theories, if I go back to the Lagrangian, where is the Lagrangian? Here. So if you think about the axion decay constant in that Lagrangian, it's really M Planck divided by tau, right? And tau was 10 to the
in this
28.
theory, yeah, but I mean, I'm asking the previous, but okay, let's discuss this one as well. Sure.
Right, because I think this is the place where your point is the strongest. So you could have looked at this Lagrangian and said, well, I'm telling you the decay constant is M Planck over tau, and if tau is 10 to the 28, that's like an electron volt. So that means that something has to happen at the electron volt scale. And so and that's basically right. There's two levels of thinking about it. So you might have thought that it's worse than that. It's not just something has to happen, but that things are strongly coupled at the electron volt scale because the decay constant is electron volt. So if you're at electron volt scales, your effective theory broke down. That actually doesn't happen. So this thing matches on to, so something has to happen at the electron volt scale. That's right. But that's actually where supersymmetric large
tau gets alive. Here it's easy because here tau gets alive. It's like sigma integrated in from the point of view of QCD, right? It's really similar.
Well, I don't have to use QCD here. The statement I want to make is that there's a very off-the-shelf UV completion that happens at electron volt where two extra dimensions kick in because that's as big as they could be. And in that case, in that language, the tau being 10 to the 28 is the same thing as saying that the radius of these extra dimensions is 10 to the 14, which is what you'd need for large extra dimensions. And then the story of supersymmetry is that the bulk is supersymmetric, and then the physics of the brain is the standard model, and that's not supersymmetric. So all the things I'm using very naturally can get embedded into the SLED models that were motivated by the cosmological constant 20 years ago. And so in that framework, then the axion question you're asking, it would be one in which you've got matter in the brain coupled to this three form. And now there's some choices as to which kind of a three form. There's a variety of three forms you can get from extra dimensional models. And depending on which one you choose, the constraints on what the scales are differ. So that becomes a more of a model dependent question. But there certainly is a UV question that kicks in at the electron volt scale, but it has a natural answer. That's part of the talk that I would normally give to the string people, but I hid the slides here. But there is a story in our papers about how you can embed this into the 6-dimensional models. And that's in the end of the day, if you ask, why is the electron not gravitating? Above the electron volt scale, what's happening is it's the extra dimensional argument that the physics is on the brane and it's curving the extra dimensions and not the curvature that you see when you're doing cosmology. And in those models, the reason the people abandoned them was that they never actually had a small enough vacuum energy. And in retrospect, we now understand why, because these symmetries, when you stabilize the modulus in those things, we always used to take fluxes and stabilize the extra dimensions as a sphere. That breaks the symmetries. And so that was the mechanism that wants to suppress the energy is the symmetry. And we had chosen by accident a stabilization mechanism that didn't respect the symmetry. And so now I'm motivated to go back and rethink those extra dimensional models with the symmetries built in. And so that means stabilizing the moduli differently. And I suspect that it should be now much easier to have top-down models that have much smaller vacuum energies.
I see.
Okay. So maybe I give others an opportunity just to jump in if they had a question they wanted to ask before we...
These are great questions, I have to say.
So, I mean, maybe it's a very generic question, really. I mean, I know you sort of suggested at the end that the sort of phenomenology really remains to sort of be explored further. I mean, and you briefly mentioned these like atomic clock experiments as well as the other the tests of gravity that you're trying to evade and all of this. To what extent do you think you'd be in a position to make predictions for things like couplings to the electron or to the photon that you could give as a prediction on a parameter space for experimentalists? Because these experimentalists are often trying to motivate building, creating more precise atomic clocks and doing ambitious things like putting them on a spacecraft and sending them on a like elliptical orbit around the sun. And they would be very happy to have a prediction from someone like you for like coupling. So at what stage are you at now, and how far in the future would it, or how much extra work would it require to start to make solid predictions, or is that even possible for things like couplings?
I think it should be possible, and I'm always tempted to say, oh, it won't take very long. And then, of course, that's always the thing that's wrong. But I think the thing that stops us making concrete predictions now is we don't have one model that does everything, right? Because the thing that does the screening in the solar system has a potential, and then the cosmology I showed you that was suggestive didn't have a potential for the axion. So it'd be nice. I think one of our first priorities is to either make a screening mechanism that's consistent with the cosmology, or to see what the cosmology looks like with the screening mechanism we have, and to have one framework in which you can say, well, now in this framework, this is what you should see. But there are some things that we can say that are robust, and that is that the basic coupling, of each proton, say, to this dilaton, it literally is a Brans-Dicke theory, and the prediction is that its Brans-Dicke coupling is this 1/√6 that I'm showing here. That is something which is the core of the model drives that. So if I go to here, that G, that's all that goes into that is that the starting point when I said that e to the minus k/3 was a series in tau and the first piece was tau. Given that this expansion parameter is 1/10⁻²⁸, that tau is really all that matters for almost everything. And so then all I'm using is that and plugging it into the formulas and learning that this is the Brans-Dicke scalar and the corrections are super, super small. So at the microscopic level, I think that's just a flat prediction that that you're coupling to this thing with gravitational strength. And so the thing that's slippery is that all the constraints are seeing macroscopic couplings of macroscopic objects. And then, for example, if you look at black holes, they have zero coupling to the dilaton because of the no-hair theorem. And so if you throw a bunch of these things, these particles into the black hole and make a black hole of it, it doesn't couple at all to this dilaton. So that's perfect screening. And so we know that it exists, and it's just a question of how it works in the things that we're actually testing gravity on. And I think until we have a clearer picture of that, it's hard to make a very robust prediction that you have to see things. But it is true that it's very difficult to make the screening mechanisms because of all the constraints coming from the existing tests. And so that makes me think that it's going to be, if we succeed in doing it, we're not going to do it by a lot. So all of these things that they're doing, that the atomic clocks and the satellites, they're all going to have something that's not so far from where these models are going to predict. If that's the way nature works, it's going to have to be there, not too far from where we're looking.
Yeah, that's a very exciting prospect, I think. All right, last chance, people, to air any questions, but I didn't see anyone unmuting. So yeah, maybe